Good morning, everybody. Hope everyone's having a wonderful day. So, anyways, I'm going to be picking up where I last left off. We're going to talk more about set theory today. So, before we do anything, I need to start talking a little bit about different properties that sets have. And then we're going to use some of these properties to kind of build on our idea of the element method so that we can kind of prove more complicated statements. And then I'm going to give you a bunch of interesting identities and ultimately show you that there's actually a very interesting connection between some of the things we've seen earlier in the course with logic and the stuff that we see right now with sets. So anyways, I want to first talk about subsets. So let me talk a little bit about that. So remember, if I write down, if I give you a set A, and I want to say that A is a subset of B, that means that for all the elements that are in A, if that is the case, then they must also all be in B, right? So just keep that in mind when we're trying to show that one set is a subset of another set. So I want to talk about some properties of subsets. I'm going to prove a couple of these for you. And then we're going to go to something a little bit more complicated. So for each one of these sets, I'm going to call them A, B, and C. The inclusion property for intersection. So it's worth noting, just for the sake of time, whenever I use the symbol cap, I mean intersection. Whenever I use the cup, I mean union. So sometimes I'll use intersection, sometimes I'll explicitly write it, sometimes I'll just use the symbol just for an abbreviation. So when you're usually writing this out formally, you would actually use the words. So first, the inclusion property for intersection says that if I give you A intersection B, this is guaranteed to be a subset of A. Likewise, you could say the same thing for B. So if I have A intersection B, because they both have elements, but they both must have common elements in the resulting computation of the intersection. So it means that if I have both elements of A and B together, that means that it cannot have extra elements that are not sitting in one or the other, right? So likewise here, A intersection B is in fact a subset of B. So we're going to actually prove that in a moment. So likewise for union, we have something very similar. So if I give you a set A, I can always tack on another set using union. So if I have A, I can always take and show, hey look, it's always a subset of A union B, where B is another set. So you can do the same thing here with B. Lastly, we have the transitivity property. So if A is a subset of B and B is a subset of C, then naturally because of the transitivity property that we would like to have, A is a subset of C. So why does this matter? Well, remember that these are nice building blocks that we can use to kind of prove tougher statements for the element method. So the common proof strategy that we're going to use, and we're going to see this quite often, is that we're going to write out their definitions. We're going to try to do this procedurally, and then we're going to see what we get if we can start using the bits and pieces of the definitions and try to combine them in some way so that we can get what we ultimately want to prove. Sometimes it doesn't come out very nicely. Other times you carve a few extra steps to kind of put together parts of sets to get new sets, and then we can talk about what those sets actually mean, and that's usually our ultimate goal. So you're going to find that that pattern is very common throughout this entire lecture. So first I'm going to prove for you that A intersection B is a subset of A. So remember, I told we're going to just use the element method. We're just going to consider an arbitrary element in the set, and we're going to just prove directly that that if I give you any one of these, that I could basically recombine them using definitions to ultimately show you that the relationship holds here. Now, remember, this says subset here, not equals, so there is no two directions to this proof. There's only one. I just need to show that one is a subset of the other. If I had this as, which I don't believe that this would necessarily be true unless B was very particular. If it was A intersection B is equal to A, then I would have to show A intersection B is a subset of A, and then I would have to show A is a subset of A intersection B. But remember, that's for a very particular B. We only know this property here just for general sets with a subset relation like this. So I'm just going to start off with what I've been doing already. So I just suppose that there's A and B. These are arbitrary sets. And then I'm just going to consider any arbitrary element that is in the resulting set of the intersection, which is, remember, this is the part that I'm given, and I want to ultimately show that X, this element, is in A. So, by the definition of intersection, well, remember the definition of intersection says that X has to be both in A and in B, right? It has to be both in A and B. So I'm just going to write that as my next part here, because I'm just going to use the definition. So by the definition of intersection, both X is in A and X is in B. Now, the most important thing here that we have is that X is in A, right? This part in particular is very important for us. So in particular, X is in A. But guess what? Guess what? This follows all in line with what I was just saying a moment ago over here. So if I just showed you that X is in A, right? It's right there. So therefore, by the definition of subset, X is in A intersection B, right? But I already told you that, hey, look, it's both X is in A and X is in B, but we know that has to be X in A, right? Otherwise, this would not be true, because both of these have to be true in order this to be the case with the intersection here. Thus, I can say A intersection B is a subset of A. Nice and straightforward, right? It's kind of cute. I'm going to prove another one. So why don't we prove the second one here, the inclusion of union? I'm going to write out what I'm going to prove. So let's write out what I'm going to prove. So A is a subset of A union B. So that's what I'm going to prove for you right now. You're going to find I'm going to use a pretty similar strategy. So do notice that this has a union on the right-hand side of that subset symbol right there. So that's going to come into play here. So I'm going to do the same thing I did before. Suppose A and B are any sets. Let X be any element in A So I'm just doing the same thing, it's the same setup here. So I'm just considering any arbitrary element that's in the set here, just like I did up here. So, what am I going to do now? Well, let's think about this. What would it mean for X to be in A union B? Why don't we think about that? So let's just see what that means. So I'm just going to say, notice that. Notice that for X in A union B to be true, by the definition of union, it the definition of union. I'm just using the definition. There's nothing going on that's very strange here. I'm just using the definition of union to tell me if that were true, what would that mean? Well, this is the great part. Well, look at this. Look at this. I took and made x to be any element in A. But remember, for this to be true, it needs to be that x is in A or x is in B. At least one of these two has to be true. And guess what? It's right here, right? I just told you that x is any element in A, right? And that means x is in A. So, since x is in A, it follows that x is in A union B. Therefore, A is a subset of A union B. End of proof. We're done. We have demonstrated for which needs to be proven. See, it wasn't too bad, right? I'm just using the definitions. And then I just use the bits and pieces that I find. And hey, look, there it is. I'm going to show you one that's a little bit more complicated. So this one is actually going to be me using the element method. And I'm going to try to show that if I give you some set with some operations done to it, that it is equal to another one. So, in particular, I'm going to prove the following. So this one's not involving, well, technically, it's two subsets, just one direction than the other. So I'm going to prove something called the distributive law for sets. It's worth noting that this one isn't necessarily as tough as the one I gave you on the assignment. So don't worry, it will not be as involved as this, but you still have to, remember, work through this process where you're just thinking about what the definitions mean, then you take the relevant bits and pieces that you get. Remember, keep in mind when you say and versus or if you're using the complement, what it means to say not. These are all very important things. So let me state the distributive law. So this one's going to be a bit of a mouthful. So if I give you three arbitrary sets, A union B intersection C, like this, this is going to be equal to A union B intersection of A union C. So this is the statement. So I'll give you three arbitrary sets. This property holds. This should look very familiar to you in terms of the ideas. We talked about distributive property in the past. This is involving sets. So let's prove it. Suppose A, B, and C are any sets. They're just any sets. I'm just doing what I did before, right? Because remember, I'm talking about a universal statement, so I cannot just fix just one of these and just say, hey, look, I showed it just for this one particular set. No, you have to be able to have your argument generalized to any arbitrary set. Remember that. Because remember, we're still talking about universal statements here. So, I'm going to break it into two pieces because I want to show that the results of this side is equal to this side. So remember, by the definition, I got to do it in two pieces if I want to do this directly by the element method. So I'm just going to break it into two parts. So part one, I'm going to show, so this is me I want to show that A union B intersection C is a subset of A think about this carefully. This looks a lot more complicated than the ones we've done in the past, right? So we need to be very careful. So, because that looks a lot more daunting than the things we did last day. But remember, just break it into its pieces, and then we're going to tackle it directly. So I'm going to do the same thing I've been doing every other time. Consider any x in A union B intersection C. Right? Because I'm given, I know that x is going to be in this one. I need to show that it belongs to this one, right? So consider any of such ones. By the definition of union, because remember there's a union sitting right here. A union B intersection C. Remember, at least one or the other, right? By the definition of union, x is in A or x is in B intersection C. It's one or the other, right? But it could be both, technically, right? As long as one of these is true. But, however, I don't know which one it is true, right? So I need to consider both cases. So I'm going to break this into two cases. Case 1. So this is going to be when x is in A. Since x is in A, then by the definition of union, so remember whenever I write the symbols, you'll put the words down. I'm just saving a little bit of time here. By the definition of union, both, now this is where it gets kind of neat. I'm going to use union twice. So be very careful. I'm not like taking intersection or something. I'm doing or and I'm applying that definition twice here. So both, now remember, if I know x is in A, and remember we proved this property over here, right? We showed this. So if I have A, I can really just add on another set, right? So I'm just going to do that. I'm just going to tack it on there. So both x is in A union B, and x is in A union C. So both these are true. So both x is in A union B and x is in A union C. Both of these are true, right? So we got that with our disposal. But here's the great thing. Okay. So if I know this and that, both of these are true. Well, what's the definition of intersection, right? Let me look up here. Okay, let's see. So I have both of these. Okay, A union B and A union C. Where are those? Look, they're right here, right? A union B and A union C. They're right there, right? This is easy, right? Look, I got an intersection here, but I know both of these are true. So let's just use the definition of intersection. Thus, by the definition of intersection, x is in A union B intersection A union C. We're done the case. That's case number 1. one. Case number one. Now we just got to do the other one. And you're going to find I'm going to do something quite similar to this. But we have to be a bit more careful, right? Because this isn't just a single set that I'm playing around with here. Now I have two of them. So it means I need to be a little bit more careful. Okay. So we got case 2. So case 2, this is where x is in B intersection C. So we're case number 2. Because remember, if we could show this and that, we're done for this one side. So, as x is in B intersection C, by the definition of intersection, x is in, now look at it, remember I have this and that, right? X is in B and x is in C, right? We have both of those at our disposal. That's the great thing about intersection. You sort of just get both of these to play around with. Now, since x is in B, let's think about this. So I want to use B somehow in a little bit of a clever way. Since x is in B, okay, x is in B, right? I can do a trick that's kind of similar to what I did before, right? I'm just going to tack them on, right? I'm just going to tack on what I need. Since x is in B, then by the definition of what? Union. The definition of union. X is in which sets? It is A union B. Remember, I'm tacking on A. I'm getting A for free here. It's on sale. So I get it for free here. Likewise, x is in C. So x is in A union C, right? Just doing the same thing. Hence, what can I do? Well, remember, it's both of these, right? I can just combine these two things. Hence, by the definition of intersection, x is in A union B intersect A union C. And we're done. Now it's worth noting that if I want to be a real stickler, I technically have two cases here, and I have a part. So I need to make sure I give a little conclusion for this part. Thus, that's pretty horrible looking. Thus, the statement is true. It's true in both cases. Both possible cases. So that's part one. You see this a little bit more engaged here, so we have to be very careful. So now I have to do part two. part two? Part two is me saying, hey, look, I need to show that A union B intersect A union C is a subset of A union B intersection C. Right? That's what I need to show for my next part. Let me pick that piece of chalk that I dropped. So, anyways, you're going to notice that I'm going to do something quite similar. I'm going to be a little bit more crafty here. Let X be in, remember I need to define what X is, right? Let X be, what do I want it to be, right? Remember, I want it to be this, right? I want it to be belonging to that set. A union B intersect A union C. Right? Now I'm going to do something a little bit careful here. So this isn't something I just pulled out of my butt, right? This is something that I've thought about a little bit carefully here. Notice that both of these here have A in them. So what I'm going to do is I'm going to look at two possibilities. Now, X could technically be in A, or it may not be in A. However, it's very possible that X could still be in this set. For example, it could technically be in B. Likewise, it also could be technically in C, right? So, if I want to just fix it on one of these sets, I have to consider when it's in A and when it isn't A. So, here we go. We will consider two cases. X is in A and X is not in A. So just as a reminder, remember, the reason why we need to check when X is not in A is because it's still possible that X is in that entire set, but it's not in A. Because it could technically be in B, and it also could technically be in C, for that to be also the case. So here we go. So I'm going to consider two cases again. Case 1, so this is when X is in A. Now, I chose this because I thought it'd make one of these cases really easy. Well, this is the great thing. As X is in A, then by the definition of union, let me make that a little wider, more like a cup. By the definition of union, look at this. I remember, I want to show that X will belong to this set, right? Well, if I know it's X is in A, right? I can just tack on B intersection C, right? This is easy. By the definition of union, X is in A union B intersection C. That's very simple, right? I just tacked on B intersection C. Now this is a case that, it's not as fun, but it's still not non-trivial. Since we know X is in A union B intersection A union C, it must be that both X is in A union B and X is in A union C. definition of intersection. Why do we do that? It's because remember, I have, for this to be true, right, it has to be that both x is in this one and x has to be in that one, right? That's all I'm using. So I'm just extrapolating. Remember, I said procedurally break down the definitions and then take the interesting bits and combine them into something that you can actually prove the claim. So I'm kind of taking this complicated thing and I'm breaking it down over the intersection here because those are in parentheses. And then notice that now I have two statements I can work with. As x is in A union B, then x is in B since x is not in A. So remember, for this to be true, it has to be that x is in B, right? Because remember, x is not in A. That's the case that we're considering. So as I told you, for this to happen, you're going to need it to be in B. Likewise, we're going to see, again, the same idea apply in a moment. Likewise, since x is in A union C, then we're going to say the same thing here, except it's about C. So then since x is in C, but x is not in A. Right? Remember, that's our case here, which is the one I broke down for you a moment ago. This is exactly the pieces we need. Then, so I'm just going to take the relevant bits of information that I have. Hey, look, I know that x is in B, and I know that x is in C, right? So I'm just going to look at this. Okay, I need to show that this is holds, right? Remember, this is a union here. At least one of these two has to be true. But not true, it should have the element x. I'm getting a little ahead of myself. So, if I know x is in B and x is in C, we can see what we can do here. Let's try it. Then since x is in B and x is in C, by the definition of intersection, x is in B intersection C. Thus, by the definition of union, remember, I'm just going to tack on A. By the definition of union, x is in A union B intersection C. There we go. See, look. All I did was I just broke down the definitions procedurally until I got to a point where I got enough information to combine the pieces that I needed based on their definitions so that I can ultimately get to the conclusion here. So, like before, I need to have a statement saying, hey, look, I'm going to put these together and say, hey, look, this looks okay. Therefore, the statement is true in either case. Now, I'm just saying statement. You could technically write the set theoretic relation that we're trying to prove in part 2, which I would probably prefer if you wanted my honest opinion. Just for the sake of time, I'm just going to be a little sloppy there. Okay. Guess what? I'm done, right? I just have to give my conclusion because I've shown both parts, right? Therefore, A union B intersection C is equal to A union B intersection A union C. Getting a little ahead of myself. A union C. And we're done. Woo! There we go. We did it. So, we have a bit of time here. I'm going to now show you another way you can use the element method, except I'm going to talk about empty set for a moment. Because very often you want to show, with very complicated properties, oftentimes you want to see if the set is empty or not. So I'm going to show you a very crafty way you could come up with using this element method. And you're going to find this nice and slick because I don't have to do all this extra work. Because remember, I'm just proving it directly. That's all I've been doing up to this point. So element method with empty set. So I'm going to give you the idea. So here's the idea. To prove a set X is equal to the empty set, prove that X has no elements. So prove that X has no elements. So you can do this directly in the exact way I've been doing it up to this point, but I'm going to show you a slicker way to doing this. Now remember, X can either be empty or it will not be empty. There's only two possibilities here, right? So we're going to use this to our advantage. You can suppose X has an element. X has an element. And try to derive a contradiction. So it's worth noting that, of course, you can use proof by contradiction in general settings, but keep in mind that this technique works especially well with empty sets. Because sometimes it really is just worth it to kind of just drill through this using first principles. First principles, I mean the most elementary basis for which you could reason. So I'm literally using definitions. So I'm going to show you what you could do with this idea. There is a claim. The other reason I want to show you this is because it has also a conditional statement in it as well. So claim, if A is a subset of B, and B is a subset of a C, so this set is called C, and it's taking the complement of that set, lowercase c. Then A intersection C is equal to the empty set. So that's the claim. So I'm going to try using contradiction here. So I'm going to assume otherwise. And remember, that is still a universal statement. So I can take my hypothesis as given. And then I ultimately want to show when obviously I assume that the conclusion is in fact false. So that means I just got to negate its reasoning overall for the entire statement. So here we go. Here's a proof. So assume otherwise, right? That's usually how I start this off. Assume otherwise. Just like, hey, look, I could have chicken tonight. I could have, I don't know, I could have pizza or something. But assume otherwise. Assume otherwise. So assume otherwise. Suppose A, B, and C are any sets such that A is a subset of B, right? That's sitting right there. And B is a subset of the set C, but it's complement, right? Don't forget the little c there. So, but I'm not quite done, right? Like I still have to, this is one part of me negating the universal conditional statement, such that this, but, which remember, but is and, but I like to write it this way because it just kind of flows a little nicer, but you don't have to do it this way. But remember, I need to take the negation of the part after the then, right? So A intersect C is not equal to the empty set. So what are we going to do? Okay. So what I'm going to do is I'm just going to take all these bits and pieces and show you a very clever way that you could arrive at a contradiction. So here we go. Then, so remember, what does this mean? I've got to write out what that means. Then, there is x in A intersection C. Remember, I'm assuming there's some element that exists in this resulting set. And by definition, both x is in A, right? Because both of these have to be true, right? Am I saying it right? I'm saying A and C are sets, right? I'm getting to this in a moment. You're going to start seeing some strange parallels, and I'm going to widen this lecture up actually with that. So both x is in A and x is in C, right? Let's think about this. Let's see. Now I'm just going to use what I have here. So just chalk this bit right here. Put that in the back of your mind. Just keep that in mind that x is in C. Since A is a subset of B, x is in B, right? By the definition of subset, right? Remember, we know this by definition. If it's in A, and I know A is a subset of B, that means x has to also be in B, right? That's from the definition of subset. Since x is in B, but also I'm going to involve this. Remember, I have this also to work with. I have that part involving the complement up there. Also, since B is a subset of C complement, then x is an element of C complement by the definition of subset. You might actually even look at this and say, hey, look, that looks awfully like the transitivity property we were talking about earlier, right? So, now let's think about this. Okay, x is in C complement. What's the definition of C complement? Okay, well, C complement is the set that does not contain everything that's in C, right? All the elements that are in C, it's none of those, right? So let me write that down. So this gets very interesting. By the definition of complement. And remember, complement, this is not, you look lovely today. It is not that kind of complement. It's complement with an E. By the definition of complement, X is not in C, right? Like I said, it's C complement. It's every element that is not in C. But what does this mean now? Okay, well, thus, X is in C, and X is not in C, which of course is a contradiction, right? And we're done, right? Isn't that nice? That's actually kind of cute, right? I didn't have to do anything too crazy here. I just assumed that the original statement was false, and then I just negate the statement. Thus, if the negation, of course, is true, then obviously, okay, sorry. If the negation is, remember, I want to get one step ahead of you so that you can correct me, hopefully. If I assume the other way around, I assume the statement is false, it means the negation of it has to be true, right? But I've shown you that the negation absolutely cannot be true, right? It's a contradictory statement. So, where are we going to go from here? Now, I have a brief bit of time here for a little bit of discussion about something. I'm going to write down some set identities. And I'm going to kind of walk you through some of these, and I want you to try to look for a pattern. Something that you may have seen in the past. So the whole exercise is not about me writing down the identities and making you memorize them. That is not what this activity is about. Because even on the assignment, I don't ask you to use these identities. I just want you to see something that's interesting here. However, these are very useful to know, and you can do quite similar things that we've done in the past to prove directly through these identities. Just like in the past when we talked about logical equivalences. With set identities. So, just to remind you, or if not, here's basically a high-level definition of what an identity is. It's usually considered an equation. An equation that is universally true. Universally true for all elements in some set. So, for example, if you're thinking about an identity, imagine I give you two real numbers, A and B. One common identity you might be familiar with is the idea that I can take A plus B and I can rewrite this as B plus A. And this statement is in fact true for any two real numbers, right? So this would be an example of an identity. So, let there be sets A, B, C, where all sets are subsets of a universal set. So remember, I told you that the universal set doesn't literally have to have every possible set in it, but if it helps to think about that, you can. But keep in mind that there's a lot of interesting discourse about the idea. So usually you can think about it in terms of the set that for which the discourse is happening. So remember we talked about interval notation, and I talked about the discourse being their real numbers. So in this case, I'm just going to make the universal set just some set that is a superset of all three of these. There are certain kinds of universal sets that just can't exist. Depending on how much time we might talk about that next day. Not sure. So anyway, let me just start this little exercise. Commutative laws. So if I give you two sets, A union B is of course equal to B union A. Likewise, A intersection B is equal to B intersection A. These ones should be pretty straightforward to see because, now remember those are the forbidden words that I keep saying you should avoid using, but these are literally from the definition. I'm just permuting the ors and the ands in the definition. I Again, that sounds awfully suspicious when I say that. Associative laws. Associative laws. So the associative laws. So if I give you A union B union C, this is equal to A union parentheses B union C. So I can just change which are ordered by their parentheses. Likewise, I can do the same thing with intersection. A intersection B intersect C is the same as A intersect B intersect C. Now, I already told you the distributive law. For the sake of time, I'll let you just copy that here. So distributive laws. Okay, identity laws. Okay. A union the empty set. Okay, the empty set has no elements in it. If I take the union of A with the empty set, I should just get back A, right? And if I take A, intersect it with what? The universe. A intersect the universe. That's pretty mind-blowing if you think about it. A intersect the universal set. If I take this, remember, it's only the ones that belong to both, so this would just end up being A. Because A is the smaller of these two sets, if you think about the size, unless A was equal to the universal set. Which in that case, this will still hold, right? Okay. Let's talk about complement laws. Okay, complement laws. Okay, if I give you A, and I take its complement as the other term in the union, this is, of course, remember, A complements everything that's not in A. So if I take both of these together, I should get that universal set. And if I take A and I intersect it by its complement, then I should get what? Okay, well, A complements everything that's not in A, right? So these two sets are disjoint and thus equal the empty set. One thing you might find helpful for the assignment is called the double complement law. The double complement law. This is, if I take the complement of C and then I take the complement of that, I should get back A. Because remember, if I take the complement of A, that's every element that is not in A, but then I take the complement of that, so it's everything that is not in the complement of A, thus that must be just A, right? Okay, another one. I think I got this right. Idempotent. Idempotent laws. So if I take the union of A with itself, I should just get A. If I take the intersection of A with itself, then I should just get back A, right? You can see how you can prove these using just definitions, right? So, we're just about done here. You're going to start seeing, I don't know if you see the pattern yet. You might need to recall back to assignment 2. Okay, here's another one, universal bound law. Universal bound law. I will make it laws because I think I have two statements here. Okay, if I take A and I union it with the universe, then I get universe, right? Because universe is bigger. It's either going to be the universe or it's going to be a set that has everything including A in it. Likewise, A intersecting the empty set. Remember, empty set has no elements in it. So that means that they have nothing in common. Okay. Here's one that's going to stick out to you like a sore thumb. Or a surprise, like on a birthday. Okay. There exists De Morgan laws on sets as well. So if I give you A union B and I take the complement of this, this is just going to be A complement intersect B complement. So I'm just going to end up with the complements contained and combined with an intersection. Likewise, you also get this one. If I have A intersection B, and I take the complement of that, this will end up just being A complement. Should it be or and? Let's think about this. I see a small thing here. Pretty sure that this is supposed to be an intersection, right? Always remember, read very carefully when you're going through and trying to use a property. So, yep. So you'll notice that this looks awfully familiar, doesn't it? I'm going to make it click very shortly. So there's three more I'm just going to quickly jot down. The absorption laws. The absorption laws. Okay, if I have A union A intersect B, where A intersect B is in parentheses, just as this equals A. Likewise, A intersect A union B is equal to A. Then there's some complements. Remember, these are not, hey, you're looking wonderful today, or, oh, those cookies look delicious. This is complement with an E. Complements of U and the empty set. So the universe's complement is in fact the empty set, because it's everything that is not in the universe, which is just a set with nothing in it, right? With no elements. And the complement of the empty set is in fact equal to the universe. One last one, and this one is going to kind of help me get to the next point of my reasoning. It's called the set difference law. Okay, A set minus B is equal to A intersect B complement. So any term that you have that has a set difference, you can rewrite it using intersection and a complement. So these are all the main laws. See, like I just have a big list of these. I'm doing this for a very good reason. Here is it. So you can see that I can get rid of set difference by just simply rewriting it in a bit more of a, it's obviously a little bit more tedious to do it, but it's possible. But you'll notice that these sort of have a strange pattern to them. So one thing that's worth noting just before I get to that is remember, if these two sets are equal, that means any element that's in one of these, it must also be in the other one, right? Just keep that in mind. So I want you to think about this, okay? Take a look at, let's make this a little easier, that's the universal set right here. This is just the universe. Okay, if you look at our list here, if I give you the universe, you notice that everything is contained in the universal set, right? It's kind of like if I gave you a tautology. If you look at some of these laws, the way the universe operates, it operates just like a tautology. Likewise, the empty set operates a lot like a contradiction. Notice that anything that it usually gets played around with the empty set usually ends up being the empty set, or if it's not relevant, it becomes just not relevant. So for example here, if I take the intersection of A with the empty set, you'll notice that it's the empty set. But notice, I'll kind of start drawing this out for you. Okay, look at De Morgan's law here. Okay, does this look familiar to you? It's like I almost showed you this, but in a different language, right? Notice that if I were to replace these complements, these C's, with tildes or knots, if I make those knots and I change these from sets to, say, for example, variables, and I were to take these union signs and these intersection signs and I bang them in with a hammer, like just imagine I took that U, and it's like taking that union and I'm just going boom, boom, just pounding that in so it's nice and sharp. This should look awfully familiar to you. This just looks like the one I gave you for propositional logic, right? So if I give you the complement, this is quite, it has like a parallel, right? So the complement looks kind of like this, right? It's like not. It looks a lot like not. And like I said, look at our De Morgan's law there. If I give you union, that sure looks a lot like or, right? Remember, I bang it in with a hammer to straighten it out. Naturally, you might look at intersection and look at this and say, hey, look, that's wedge, right? That's and. Well, what about set difference? What's set difference? Remember, I told you that anything that's a set difference can be rewritten like this. So, guess what? Set difference is covered, right? So, everything I have over here is kind of in our set theory land. So, this is a formulation in set theory. And this is our we got two worlds going on, and guess what? They correspond to each other. It's almost like there's some overarching structure that I'm just not telling you about. So both are special cases. So the way that we use these operators are special cases of the same general structure, right? Same general structure. This is called a Boolean algebra. So you can actually create an algebraic way of talking about all of this in terms that I'm going to give you kind of an idea of. I'm not going to talk about Boolean algebra in depth here, but you basically have all the bits and pieces to actually understand it very clearly. So there's a correspondence between the set theory that we've been talking about and the logic we've been talking about. So just give me an example what I mean. If I say X is in the set A union B intersection C, say if I knew that this was true, I can also rewrite this in a different way. This is true if and only if X is in A, right? That's that part right there. So I'm just going to put X in wherever it needs to be. Remember, I told you union is kind of like or, right? So I put or there. And then I have X is in B. And X is in C. Look at this. Look at this. So you'll notice that if this statement is true, then that one has to be true, right? Likewise, if this one is false, that one is false. Now, just to kind of put the cherry on top, okay, instead of just using X and A everywhere, give this a name, like call it like P. You could call testing if, call it like Q, might call that R, might call them A, B, C. They're just some variables. They can be either 0 or 1, where 1 means true, 0 means false, and then naturally you can evaluate these statements with logic. So if I give you a set theoretic statement, I can actually convert it to a statement of logic and test it in that way. So it's a very powerful idea. So you can replace these set theoretic entities with logic like this. Likewise, you could do the opposite. Like I could take something that's written in logic and write it in set theory, which is quite powerful in its own right. So you might ask, Dan, why is that relevant? Like, why should I care at night? Like, when I go to bed, I think about this at night. Why should I care about this? Okay, well, oftentimes we're here and we want to learn about why things are applicable to us in society at large, or learn about the universe. Okay, so one thing I didn't have really much of a chance to talk about is that every one of these kind of statements that I have over here, they can be written in terms of a Boolean algebra. And a Boolean algebra can be, basically it's the starting point and foundations in terms of the mathematics of digital circuits. So when we talk about different gates inside of circuits, the mathematical basis for this is in Boolean algebra. So all these things I'm looking at over here, those are all things that the logic that follows underneath your hardware in terms of the digital circuits, how they actually operate. So it's a very deep thing to think about. Remember I talked way back, I talked a little bit about Claude Shannon, right? So this is basically what I'm talking about. So he was able to show that this so-called Boolean algebra is equivalent to the digital circuits that he was operating on, which kind of came up with his most amazing master's thesis ever. So That being said, just remember that in Boolean algebra, normally these variables will have a value of 0 or 1, and the operations of and or, they'll usually represent it as a plus or multiplication symbol. But keep in mind, I'm not going to test you on Boolean algebra, but I just really want to give you this insight. It's a very powerful one. So, that being said, we're going to stop here for today. I want to say thank you very much, and have yourself a beautiful day. I'll see you later.